All right, I hope everyone had a good break. Just before break, we had been looking at several examples with the Heisenberg possibility principle, and this most recent one was talking about this J psi meson discovered in 1974, and kind of has an interesting history to it also. I had mentioned that this, all of the really detailed properties of this particle were mapped out at the Stanford Linear Accelerator Center, where I want to say the discovery was actually made. It turns out that there was a competing scientific group on Long Island at Brookhaven National Laboratory that had a different sort of accelerator trying to make the same measurement. It was a proton, anti-proton accelerator, which made it really difficult. So what they were trying to do was discover this particle. This had been predicted by theorists. It was actually the charm quark, if you're familiar with quark model. This was one of the first predictions of the quark model, and it turned out to be a good prediction. All of these particles containing charm quarks were discovered. Anyway, this research group found out that Stanford Linear Accelerator Center was just about ready to start collecting data, so they went ahead and held a press conference and claimed they had discovered the particle. People still argue to this day. It's kind of an East Coast, West Coast argument, I guess, about who actually made the discovery. In any case, the people at Brookhaven called it the J, and the people at Stanford called it the psi. And so it is, to this very day, 45 years later, 47 years later, it's still referred to as the J psi. It has not been resolved as to who gets credit for the discovery. All right, so quantum mechanics. One of the big deals about quantum mechanics is that instead of particles following one definite path, they can follow many paths. Instead of a particle being at one certain location, it could be spread out. There's going to be some probability of finding it over some range of locations. Instead of it having definite energy or definite momentum, it could have a range, it could have a combination of different momentum or different energies. And so classical physics is kind of based on the idea of things follow definite trajectories. Quantum physics, many possible paths. Now, this last sentence here, quantum mechanics is very different. You can predict what many electrons, they shouldn't use the word masses of electrons. Masses of electrons means something different in physics than masses of electrons doesn't mean many. That needs to say many. What many electrons will do, but you have no idea what any individual one will do. That's not really true. Quantum mechanics is very clear about what possibilities there are and how likely each one will be. So a good example of this would be, think Las Vegas, right? If you go to Las Vegas and all those casinos, all the people operating the casinos, they know what the probabilities are for every game that people can come in there and play. If they're playing cards, if they're playing slot machines, they know what the probabilities are. They know all the possible outcomes, and you can actually calculate at what rate, the house will start making money when people come in and start gambling. So quantum physics is kind of like that. We can identify up front, there's many possible paths, but we can identify what are going to be the possible paths, and then we can calculate what the possible outcomes will be. Now, they are introducing the Schrodinger equation here. We already took a look at that, so we're already Schrodinger experts here. And they said that if it's a traveling particle, a particle going from A to B, energy is conserved, and they're claiming here that therefore the wave function will be some combinations of sines and cosines. Now, the problem with sine and cosine functions is that they're not definite momentum. They're not definite momentum particles. So they're actually going to be combinations of different momentum, and that's fine. But these are already what we call linear combinations because they contain different momentum to them. So just something to be aware of is that these exponentials are more fundamental functions to be using rather than the sines and cosines. The Schrodinger equation looks like this. This is written backwards from what we did. We said energy is equal to, there's kinetic energy, there's potential. Here is the energy. Now this is the time independent. They're not including timing effects here. We could lose the period. And then here's the potential energy times the wave function. And then here is the kinetic energy, right? That's momentum squared because we're taking two derivatives with respect to x. Now, here's another thing we already talked about too, and that is if we want to calculate the total probability of finding the particle at any location, what we can do is we can square, or more specifically modulus square, the wave function and then integrate over all possible locations. When we do that, it needs to add up to be 1, or it needs to integrate out to be 1. So we call this process normalization. We say that the wave function is normalized when this condition holds. All right, here is the more general time dependence. So we put here, they put the time dependence back in to the wave functions. You can see now it depends on x and t, compared with before, where it was just depending on x. Here they were using derivatives just in terms of x, and in the time-dependent case, they've switched over and used partial derivatives with respect to x and partial derivatives with respect to t. Now they're saying this equation cannot be derived. Sure, we sort of derived it by looking at what would we need in order to represent a particle, in order to represent its momentum and its energy, and keep track of interference effects, keep track of wave or phase effects, and that's what this equation does for us. Now, when we do have solutions, wave functions, that involve x and t, pretty much in general, that can be separated out into functions of x and functions of t. Now, sines and cosines are actually a counterexample to that. A sine or a cosine, traveling wave, cannot be separated out quite that easily. Okay. Now, what happens with the time portion, I guess we looked at this already, tends to be e to the minus I omega. That's omega, right? The frequency is given by e over h bar. So it says typically when we're using the time-dependent formula, that's what gets tacked on to the expression. So here's what the textbook is going to tend to do. For the x-dependent dependence, they're often going to come back to this sine-cosine expression where the kinetic energy is related, or the wave number is related to the total energy. We'll see how this derives. In fact, let's try it. So here's an example. Let's say we have an electron. It's a free electron. The electron has an energy. Now, when they say the electron has an energy 6.3 eV, we have to decide, well, how much of that is kinetic and how much is potential. Now, in this case, they tell us that the potential energy is 0. So that means that is all kinetic energy, and the mass energy is not being included at all. So just to be clear here, this is not keeping track of the mass. The mass energy for the electron would be 511,000 eV. Now, they want to know what the wave function should look like. Now, they're going with this sine and cosine stuff, but let's see if we can do exponentials instead. So what they said was that the potential energy is 0, So everything we're looking at is kinetic energy. The mass energy for the electron is 511,000. And so what we want to do to get the total energy is, now this total energy is the relativity total energy. We want to combine the kinetic energy and mc squared. Well, when we do that, it still rounds out to be 511. I mean, I could have written this as 511,006.3, but to 3 significant figures, it really didn't change. So I went ahead and just left it at 511,000. And then I divided through by h bar. The h bar in eV seconds that we had looked at, 6.59, 10 to the minus 16 eV seconds. And I got a frequency of 7.75, 10 to the 20th radians per second. Now that's the wave function that I suggested we would be using. And what I needed to be able to calculate was the omega, and now we have the omega. Now this is a wave function with a definite energy and a definite momentum. We found the energy and we plugged in the omega. Let's see what the momentum will be given by. Now, for a Schrodinger equation example, the kinetic energy is given by p squared over m. So I apologize, these e's are the e from the Schrodinger equation, which are really just kinetic energies. But these e's over here are from relativity statements of mc squared plus k. And it's the total energy, including the mass of the particle, that needs to go in for the calculation of frequencies. Okay. All right. So I took the physics 4a and the Schrodinger equation version of kinetic energy and solved for momentum. And then I put some factors of c in. So when I did that, I got that Pc is 2mc squared times the kinetic energy. That comes from this statement right here, square rooted. I plugged in mc squared, I plugged in the kinetic energy. Turns out the momentum here is just 50 eV. It's a pretty slow moving electron. So the momentum is really low. I can get the wavelength by taking hc over pc for this electron. So this electron has a wavelength of 24.6 nanometers. And then I can get the wave number by taking 2 pi over the wavelength. And that gave me 2.55 10 to the 8th radians per meter. So you can see the omega and the wave number. Once we've got those, we've solved for our wave function. Now we haven't normalized the wave function yet, but that's fine. Okay, we don't necessarily need to normalize. In fact, with these simplest wave functions, we've already tried normalizing and found out it's actually predicts a particle that's located everywhere. And so normalization, we can't determine a constant out front. I guess I have a couple steps here too. With here the kinetic energy is much, much less than mc squared. And so I'm using this approximation, which is a Schrodinger approximation. And then momentum is 2mk. And that leads into this equation with factors of c. All right, so this, so here is kind of that standard wave function that just goes on and on forever. So that's not as realistic as something like this. So we looked at this earlier when we were looking at Gaussian functions to represent wave packets. So, but that's not a big deal for us. Be aware of what wave packets are, but we don't have any problems where we have to calculate, do any calculations involving wave packets. All right, here, up until now, we've mostly been talking about particles that are free particles. They're wandering anywhere they want to go. Let's take a look now at what is referred to as the infinitely deep square well potential, whatever that is. This is one of the examples that we can get an exact solution for the Schrodinger equation. And what it involves is this. It says that, look, there's a region of space where the particle can move back and forth freely, but it can't go outside of that region. So unlike a free particle that can just keep traveling forever, the particle in this case is stuck inside a certain region. What would that refer to? And what that could be is something like an electron inside an atom, or a proton or a neutron inside the nucleus. Now, it says that for the region where the particle is located, they're going to go back and use sines and cosines. This time that actually works pretty well. So with these particles that are confined within a region, using the sine functions in particular are really handy. So what they're going to do is require that this particle be represented by a wave function. That's how particle properties are related. And since the potential energy here suddenly goes to infinity, the particle just gets, it can't cross that boundary. The wave function has to go to zero. The probability of the particle being found at that location has to drop to zero. Now, these are kind of the results of solving the Schrodinger. We're going to do this. So we're going to go in and derive this energy formula. Now that's a kinetic energy formula. And then these are the quantum numbers describing how much energy there is in the different quantum states. Let's take a look at that. So here are what the quantum states correspond to. Here are the wave functions here in the middle. So if we have, again, a fixed region, we're going to say it has a width of L. So this is kind of interesting. What is it we need to know to define this region? Well, we're going to say that the potential energy goes to infinity at the edges. And so the particle is free inside, but because the potential energy goes to infinity at the edges, the wave function needs to zero out at x equals 0 and at x equals L. These are referred to as boundary conditions in differential equations. So we've got to meet the boundary conditions imposed by this high energy potential outside of this region. And what we find is we get a series of functions, a series of sine functions that satisfy the differential equation, that satisfy the Schrodinger equation. Now, you'll see that what's happening with the wave number, the k wave number, it just keeps increasing. Oh, this is state number, that's really state number 10? I guess it is. Yeah, okay. State number 1, 2, and 3, you can see how we're gradually increasing the wave number as we go through those. Now, this is what the wave function squared looks like. So the wave functions are here. This is the probability distribution. So remember, to get the probabilities, we have to square the wave functions. And so these are the squares. Now, there's like a 100% chance I'll ask you to draw a diagram like this, something like this, on the midterm. And you need to be clear about differences between sine functions and sine squared functions. If those functions look the same to you, look closer. See how in the sine functions things rise and fall gradually? There are no sharp edges anywhere, and there aren't any here either. It's just that this function, the sine function itself, goes to 0, and then goes negative, and then comes back to 0 and goes positive. The sine squared function goes to its peak value, comes back down to 0, comes back down to 0, but it's smooth everywhere. There's no sharp discontinuities in the function. Okay, here's what mine look like. So here's quantum state 1, quantum state 2, quantum state 3, and I imagined electrons in these different quantum states. So again, maybe it's an atom, and the electron is stuck inside this atom because the nucleus is attracting it. And so these are the possible wave functions. The possible wave functions here are, here's a normalization constant times the sine function. Now, it turns out that the possible ways that we can meet the boundary condition on the other side would mean n times pi times x over L. Now, why does that work? When x is equal to L, x over L cancels out. It just becomes 1. So if that becomes 1, then I'm left with the sine of n pi. And the sine of n pi equals 0 for all integer values of n. And so that's the form of the wave function itself. Now when we square it and turn it into a probability distribution, that's when these functions become sine squared. And so the sine squared functions start off with a slope of 0, and then they rise and they come back down, and they have a slope of 0, and they rise and they come back down and have a slope of 0 in between each one of the peaks. Now the wave function, we've been saying kind of over and over, the wave function contains all the information. But the probability distribution actually gives us a description of where the electron will be located. If we try and find out where the electron is going to be found in an atom or a molecule, it's the probability distribution that we need to look at. So all of chemical bonding, all of chemistry, to some extent, is based on this idea of quantum mechanics, where electron distributions are not just random. Electrons can't arrange themselves just any way they want. There are certain quantum states that those electrons need to be in. So the electrons have the properties of a particular quantum state to them, and these little regions where the electron is built up, those raise the possibility of forming a chemical bond. All right. In the regions where there aren't electrons, then you may not have a chemical bond being formed, or the number of chemical bonds can come down to how the pattern, the wave pattern of the electrons that you're working with. Okay, so this is really a big deal in terms of all of chemistry, right? Of everything around us, really, all the compounds that can be formed in nature come down to how these electrons get arranged. Now this is a really limited model that we're looking at right now. In the next chapter, chapter 39, after we come back after the midterm, we'll do a chapter on atomic physics and look at more detailed. Right now we're only working in one dimension, and come on, atoms aren't just one-dimensional, they're three-dimensional, and it's a really simple potential energy function. The potential energy is either turned on or it's not. It's either 0 or it's infinity, and atoms are more complicated than that. We'll come back and look and see how some of those potential energies are set up. All right, so infinite potential, these are some of the names this goes by, so you got to be ready for any of these names. It's a particle confined to a region. It goes by the name of the infinite potential well, meaning that there's a region where the potential is low, but outside that region it's infinitely high potential energy. It also goes by the name of particle in a box. So a particle is stuck inside a certain region, inside a box. Now this could be an electron in an atom or a molecule, it could be a proton or a neutron. The Schrodinger equation for this becomes energy is times the wave function. Now that's the kinetic energy term, and because the potential energy is 0 within the region, it just drops out. So here's the Schrodinger equation here, I guess, is where the starting derivation came from. So kinetic plus potential. Kinetic, we have to rewrite that in terms of momentum so that we can use our momentum operators. The potential inside, so we're exclusively looking at the region just inside where the potential energy is 0, and that drops off. These are the boundary conditions that have to be met, and it's the sign functions that are able to meet that boundary conditions. We don't use cosines because the cosines are going to go to 1 at x equals 0. Now we could redefine this. This side we've called x equals 0. This side we called x equals L. We could call x equals 0 right down the middle. And this is like minus 1/2 L and plus 1/2 L. If we do that, then we find out that we can use cosines also as solutions. But so I guess to simplify our solutions, we can just write them all as sine functions. We put x equals 0 at one side. So x equals 0 is here, x equals L is over here. What we're going to do is we're going to take the wave functions that we just looked at. These wave function of x is a times the sine of kx. We're going to take one derivative and then take a second derivative because that's what Schrödinger's equation tells us to do. So we got to get that second partial derivative with respect to x. And so there it is. Now when I've taken two derivatives, I do have the same wave function back again. So this wave function is not an eigenstate of momentum, but it is an eigenstate of momentum squared. When I square the momentum, which is basically finding the kinetic energy, then I find out that I get the same wave function back again. So once we've taken the second derivative, we can plug that back into the Schrödinger equation and show that the energy then is equal to h bar squared k squared over 2m. Now, what are the possible k values? Well, we're going to bring in that boundary condition. We've been talking about it a couple times now. So let's go ahead and solve. We want to meet the boundary condition of sine k x equals L equals 0. In order to make that boundary condition match, KL needs to be a multiple of pi. That's when the sine function goes to 0. So that says that the k value itself is n times pi over L, where n can take on integer values starting with 1. 0 doesn't work very well here. We got to start with a quantum number of 1. So it says all of the wave functions that meet these boundary conditions, that go to 0 at the edges, and satisfy the Schrödinger equation, second derivative times this stuff equals energy, they all look like this. They all look like a sine of n pi x over L. So each wave function corresponds to a quantum state that the electron could be in. The electron could be in a quantum state, the electron needs to be in a quantum state, and these are the possible quantum states for that electron. So same diagram. Here are the wave functions. You can see they're sine functions. They go positive and negative. So wave functions go positive, negative. They can even be complex. Ours are all sine functions so far. The energy that we solved for, h bar squared, k squared over 2m, we substituted in for k. This is our energy formula. Now that energy formula that we've derived, I can take the h bar and the pi and turn that into h divided by 2. So I eliminated the h bars and pi's and replaced it with h. I did pick up some factors of 2, and so now we've got 8 in the denominator instead of a 2. And the energy is going to be n squared, hc squared divided by a divided by mc squared divided by L squared. So that's quantum mechanics. So that's using the Schrödinger equation to solve for a series of quantum states and then solve for a formula that tells us what the energy will be for each one of those quantum states. Again, this is kind of a practice example because it's only one-dimensional. So these are kinetic energies that we've solved for. Now let's put some numbers in. So here's the formula. I put in some factors of C so we could use some of those shortcuts that we've been using. So for example, the HC on top is just 1240 eV nanometers. The MC squared down below, if it's an electron in an atom, 511 thousand eV. And then the only thing I'm really left with is how wide is that region? How wide is the region that we're looking at? So I picked, kind of a typical width for an atom. A typical atom might be a few hundred picometers across. So let's use that. Let's say that the electron is attached to an atom and it's got about this much room to move back and forth. Plugging all of those numbers in. Now this was in picometers, so I converted that also to nanometers to get the units to cancel out. What I got for energy state 1 is 9.40 eV. Now remember, these are kinetic energies only, and this is the general formula. The energy of the first state, 9.40 eV, but if I look at my formula up here, my general one, once I've calculated the first energy state, all the rest of them are going to have, all the rest of the quantum states will have energies that are n squared times the energy of state number 1. So that becomes a useful starting point. If I multiply it by 4, that gives me the energy of state number 2. If I multiply it by 9, I get the energy of state number 3. Now, there's some fairly profound ideas in this. Let's talk about this a little bit more and push some of the examples a little bit farther. So, all right, I'm looking at these 3 possible quantum states. I can see that these are higher in energy because they have shorter wavelengths, which means higher wave number, which means they have more momentum, which means they have more kinetic energy. So the kinetic energies of that first state was 9.4. The next state is 37.6. The next state is 9 times the first one, and this one is 16 times. So you can see how fast these kinetic energies go up, but that's a little bit artificial. It's actually happening because we are looking at a one-dimensional situation. In one dimension, when we look at these sorts of problems, we do see that the kinetic energies grow very rapidly. We'll come back and redo this example in 3 dimensions and find out that actually the kinetic energies don't grow that rapidly. They grow by kind of even spacing, or even the spacing becomes smaller and smaller. As we go to higher energies, the spacing between the states gets smaller. You can see from our diagram, I guess I tried to kind of plot this. Is that unreasonable? That's not bad. So the first state somewhere around 10 eV, and the next one somewhere around 40, and the next one somewhere around 80. You can see that the spacing here is about 30 eV, and the spacing here is about 50 eV. Here the spacing's gone up to about 70 eV. So let's see what would happen if we had an electron in, let's say, state 2, and it drops to state 1. Well, the energy of that photon would be 37.6 minus 9.4 eV. That would be 28.2 eV. That would be in the ultraviolet. And most transitions in atoms from state 2 into state 1 are going to generate photons that are ultraviolet. All right. And then I calculated that photon's wavelength. The wavelength turned out to be 44 nanometers, so a pretty short wavelength. Okay, so it's worth talking about a few things here. Let's ask this question. If I have a solid block of a metal, let's say iron, let's say I have an iron block, and I try and compress it, it's not very compressible. So a block of iron is not very compressible. Why is that? Well, what we've described here actually is not a bad approximation as to what's going on in a block of iron or tungsten or gold or some metallic solid. What happens in these metals is that all of the available quantum states are filled with electrons. And all of these quantum states have certain amounts of kinetic energy. notice that there is no such thing as a zero kinetic energy state inside the atom. Electrons in an atom are always going to have some minimum amount of kinetic energy. It can't have zero kinetic energy, which in classical physics it was easy enough to say, hey, this object's at rest, no kinetic energy. But in quantum mechanics, when we're looking at electrons inside atoms or protons and neutrons inside the nucleus, they have a lowest possible quantum state. We call that the ground state, and it always has kinetic energy to it. So, there's a least amount of energy. And then with the electrons, it turns out that every electron needs its own quantum state, and so they can be spin up, spin down. But in this case, we could have two electrons, one spin up, one spin down in this lowest, and then another pair here, another pair here. So what happens is, you've got all these electrons in these quantum states, and they can't share the states. So every electron has to continue to have its own state. What happens then when we compress the material, or try to compress the material? If we were to try to compress this region where the electrons are, all of these numbers would go up. Every one of these quantum states would go higher in energy if L gets smaller. I can see that in the formula right here. The energy is proportional to 1 over L squared. So if I packed the same number of electrons into half the length, the energy's got to go up by a factor of 4. Where is all that kinetic energy going to come from? So it seems weird that there is this obligatory kinetic energy in these quantum states. First of all, the electrons can only exist within the properties of the quantum state. And second of all, that when we compress these quantum states, all of their kinetic energies have to go up. And that's why solids are non-compressible. Solid materials, in general, are non-compressible whenever we have a series of quantum states with all the electrons filled, because compressing it would mean putting in an enormous amount of energy. You would have to put in enough energy when you're compressing it to boost all of these electrons, to allow all the electrons to stay within the quantum states that are there. And again, there's not an option. The electrons can't be outside of a quantum state. They have to have that much energy. Apparently those are the rules that everything in nature is following. All right, so kind of interesting. Next time you step on a solid, think, oh yeah, it's solid because of the electron quantum states, and because the electrons each need their own quantum state. That's what makes it difficult to compress. We could similarly do an example looking at protons and neutrons inside the nucleus. Now, this is a pretty common example that gets overlooked, I feel. We tend to think, oh yeah, protons and neutrons, they're in the nucleus and whatever. But protons and neutrons in the nucleus are in the same situation of they're confined within a region, and the width of that region determines how much kinetic energy each one of the quantum states will correspond to. So let's try the very same thing. We'll just use the very same formula, n squared hc squared a. The mc squared will change. So instead of the electron mass, I'm going to put in the mass of a proton or a neutron. Now, a proton or a neutron, they're somewhere around 940 MeV. Now, that's in the millions. So instead of using 1240 eV nanometers, we could use 1240 keV picometers, but since the masses are in MeV, I'm going to use 1240 MeV femtometers. Now, it just happens that the masses of the proton and neutron are in MeV, while the distance of the strong force that holds together protons and neutrons operates over the range of about 10 femtometers. So the distance units match up with the energy units. What we've done is we've gone to distance units that are, 10,000 times smaller. Let's say we were working in terms of picometers when we looked at atoms, and now we're looking at the nucleus, which is 10,000 times smaller in 3 dimensions, which is 10,000 cubed, which is like 1,000,000,000,000 times less volume for the nucleus. And so we're putting those units in here, putting in the 10 femtometers. I calculated 2.045. Now I rounded a bit just to make this table easier to look at the pattern. So I rounded it to about 2 million eV. So that's an enormous amount of energy. That is the least amount of energy that a proton or a neutron can have in the nucleus. A proton or neutron in the nucleus in the ground state has 2 million eV of kinetic energy. That's a lot. And if we follow that n squared guideline with the quantum numbers, we're going to find that state 2 is at 8 MeV, state 3 is at 18, state 4 is at 32. So this time, let's see what happens with a photon generated when a proton or a neutron drops from an excited state into a lower state. And this happens. So when we have radioactive decay, for example, you could have protons or neutrons dropping into lower energy states. And our prediction here is that we're going to create a photon that has an energy of 6 million eV. So these are gamma energy photons. These are in the gamma ray part of the spectrum. So, and the wavelength I got with this was 207 femtometers. So kind of remarkable, right, that we've got now these photons that are millions of eV, and you have to ask, well, why are they being generated with so much energy? It's because the nucleus is so small. And it's because, it's really because the nucleus is so small. The masses of the protons and neutrons would tend to make the photons not as energetic, but the length factor more than compensates for that. So it's a length factor really driving this. And since protons and neutrons are in such a small rate, because the strong force is so strong, the spacing between kinetic energy quantum states for protons and neutrons are in the millions of eV. And that's how energetic nuclear transitions are. All right, let's add some time dependence. So we've been looking in some detail to using the Schrodinger equation with electrons and with protons and neutrons inside the nucleus. We had solved the Schrodinger equation and come up with this wave function. What we had talked about earlier was whenever we solve for a stable quantum state in terms of x, we can always just add on a factor of e to the minus I omega t, and now it's time dependent. So it's easy enough to go from the time independent equation into the time dependent equation. The time dependent equation is going to have an IH bar partial with respect to t that is included on top of that. So the omega in here is E divided by H bar. That tells us how much energy we're going to have. And when we take partial derivatives of that wave function, it's only going to operate on this last portion. So kind of interesting that we can just tack on the time dependence pretty quickly. All right, here is an example from the book. So the book's got this example, electron in an infinite potential well. Let's see how this compares. I mean, we just ran an electron problem, see what they've decided. So they have picked a length of 100 picometers. So we had picked 200 picometers, they've selected 100, And they're saying that's about the diameter of a hydrogen atom, a pretty small atom. And then they ask about photons being created when the electron jumps from one quantum state to the next. So here's our picture of those wave functions again. Here is that region of L. We had gone through and derived this formula a couple times now. So here's one more derivation of our energy formula. So yeah, that's kind of a summary. It's actually a pretty nice summary though of what we've been through. And hey, that's not a bad idea to review this each time we do one of these problems. So we had said that these are really kinetic energies, and I know maybe it's a bother going back and forth between notation, but I feel like if I just continue to use big E all the time, you guys will forget that it's kinetic, so I have to keep reminding you. So for better or worse, the K's here and the E's here are the same thing. And so plugging in the mass for the electron, and then here's the width. This time we got 37.6, so it's about 4 times more energy than we got in our example that we had put together. And that's because they force the electrons into a smaller region. So if I force the electrons into the smaller region, kinetic energies are going to be higher. Now if I take the energy of state 2 and state 1, this is really pretty big. 112.8 eV, that's definitely far off into the ultraviolet. That's getting to be a pretty dangerous photon. And then the wavelength of that photon would be 11 nanometers. So yeah, that's a lot of energy in that photon. You figure that the spectrum of light, as long as you're in the infrared or the visible part of the spectrum, you're pretty safe with exposure because those photons can't break chemical bonds. But once you get into UV, which really isn't, UV starts out at about 3 eV. So this is a really energetic UV, part of the UV spectrum. The visible part of the spectrum is really narrow. It only runs from about 1.7 to about 3.1 eV, not even a factor of 2. But the UV and the infrared regions are defined much more broadly. It's kind of surprising that our vision does everything it can do while really only operating in a narrow range of photon energies and wavelengths. Okay, let's do a normalization constant. What we want to do is we want to do some probability calculations of these of the wave functions that we've come up with. And this is actually what they claim is going to be the normalization constant, so we'll double check that. See if that really turns out to work. So here we are in example 38.6, and what we're doing here is a process called wave function normalization. So I'm taking these wave functions, see that wave function? That's what we had come up with when we solved the Schrödinger equation for a particle confined to a region. So it's confined to region L. This is what the x dependence looked like. That gets multiplied by e to the minus I omega t. And then we can modulus square the wave function to get something that represents a probability density or a probability distribution. And if I integrate the probability distribution everywhere, it'll add up to be 1. So this is the example that we want to carry out here is integrating that wave function squared over all possible values of x. Now, we're not going from negative infinity to infinity. We're going to integrate from 0 to L because that's the region where the wave function is defined. It's not defined out in the infinite potential region. So for this, when we modulus square the time dependence, we talked about this earlier, when we modulus square this, It means taking e to the minus I omega t and multiplying by its complex conjugate. That gives us e to the 0, and e to the 0 is 1. So this goes away. And what that tells us is that the probability distribution does not depend on time. The way that the electron is spread out in this region is not going to be changing with time. It's fixed. So to find the normalization constant then, this part canceled out, the time dependence is gone, so we'll just be integrating this expression right here. This a squared stuff going on here. Ooh, let's go back and take a look at this. So make sure we brought everything along. We got the a squared because we squared the wave function. We're integrating from 0 to L, and we're integrating across the variable x. And the wave function squared is going to have a sine squared n pi x over L, so we have to plug that in. It looks good. So what will come of this is we'll solve the integral, and once we have solved the integral, then we can solve for a, and a is what we call the normalization constant. So once we've solved for a, that's it. We will have our, and see, there's the answer right there, and that matches what they got. So things are looking good, I think. Okay, yeah, I think we got that right. All right, so here is the integral that we had set up on that previous page. Now, with sines and cosines and exponentials, a common way to go in and solve for this integration is to do a variable substitution. So I'm just going to take everything that was inside that sine function, substitute it in. So I'm going to let u be equal to n pi x over L. Now that says that x is L over n pi u, which means dx, which I also have to substitute, is going to be given by L over n pi du. So those three statements represent the substitutions that I will be making. Now when I make that substitution, I'm going to get a sine squared of u, and the dx is going to bring along a factor of L over n pi du. And if I'm looking at limits, when x is equal to 0, well, u is equal to 0, so I keep the same limit there. But when x is equal to L, u is equal to n pi. So I had to change the limit up here to n pi. Now, sine squared of u is equal to 1/2 1 minus cosine of 2u. You've probably seen that in your calculus classes. It's one of those trig identities that it just seems like there's always another trig identity to try and remember. You don't have to remember that one, but that is the trig identity that we're going to be using to do this solution here. So I substituted that in. There is the 1/2 1 minus cosine of 2u with everything else included here. And so I brought out the L over n pi, I brought out the 2 in the denominator, and I'm left with a u minus 1/2 sine of, when I carry out the integration, I'm left with a u that comes from integrating the 1, and a 1/2 sine of 2u that comes from integrating the cosine of 2u. Okay, so that's where those two terms are coming. And then they need to be evaluated between 0 and n pi. And so I did that. And at 0, these things go to 0. But at n pi, u becomes n pi. And at n pi, the sine of 2n pi, it's just 0. That drops out. And what that says is that particular integral can be shown to be equal to L over 2, which is kind of interesting. And so we originally had something that looked like this. We had the a squared times this integral equals 1. So now for this integration, I can substitute in the L over 2. And I can say a squared is equal to 2 over L, a is equal to 2 over L to the 1/2. And that's it. So we've done that calculation. We have come up with the normalization constant, not just for one of the quantum states. It turns out that every one of these quantum states has the very same normalization constant. So that's convenient. We only had one item that we needed to go in and solve for. Okay, so that's probably a good place to stop, I think. Let me check the time, but I'm pretty sure that's going to wrap things up for the day. And yeah, we're fine right there. So if you guys got any questions, stop by office hours, and we'll see you guys again at the next class meeting.